Hi everyone, I hope you all are doing great and welcome to day 10 at Aarush coaching classes in the array and string mastery series, in which in the last class we have discussed and implemented binary search and saw how it can be a lightning, or I can say how a lightning fast search like binary search can be implemented over an array such that the searching can be done in log of n time instead of order of n time. And though not just in words, we saw mathematically as well how big difference of it is. Okay, so after that we saw how the idea of binary search, which was more like divide and conquer technique, can be applied on a non-sorted array as well, where some hint is given, hint when some pattern we are able to find, like what we need to do about. More like the question was finding the peak element. So for every element to check, we just had to see if it is a peak or not, and if it is not, means if it is not greater than both of its neighbor, then we were just checking moving forward if I'm going deep downwards or upwards. If it is upward, means we're in the right direction. If it is downward, means we need to go backward. So that's how, with this identification point, we were able to apply binary search to solve that problem in log of n time. With the same spirit, we are gonna discuss two more problems and see better application of binary search instead of directly searching. So one of them is gonna be search in sorted and rotated array. It is an it is more like adaptation of binary search on broken data, because though we are gonna search, it is not completely unsorted. It was sorted and then rotated array. So we'll talk more about it, what it is. But yeah, this is gonna give you some better thought in your mind about the pattern of question. Next is gonna be the woodcutter problem, where we are not gonna directly understand or get where to apply searching on. Once you get where we can apply searching, then we can probably think of if we can apply binary search or not. So this problem is more challenging in a way that the input given in the question is not something which is suggesting you to apply binary search directly on it. You have to figure something out. Okay, so we'll see about that again when we are discussing it. So why these problems matter? Because as these are very difficult problems, so they are mostly asked in the FAANG companies. So because of the FAANG frequency, which is more like they both have appeared more than 60% times in the technical interviews. Then skill progression, it elevates binary search from algorithm to problem solving pattern, and then real life applications, database search, resource optimization, scheduling. So the idea that is being applied here to solve these kind of problems will lead to these kind of applications. Okay, the real life applications. बिकॉज मोस्टली पीपल थिंक सर ये क्वेश्चन हम सॉल्व करते थे बट इसका अप्लाई कहाँ होता है, कैसे करते हैं. सो दीज आर गोना बी द सिनेरियोज इन रियल लाइफ वेयर यू आर गोना अप्लाई दीज थिंग्स to make the solution optimized. Okay, so what are gonna be today's learning goals? Today's learning goals are gonna be master binary search in partially sorted array. Okay, and next would be understand the binary search on answer pattern through those two questions. Develop intuition for identifying search spaces. Okay, because directly working with the only on the input is not enough, so that's why you would have to identify your search spaces as well, so that you can apply searching. Next, handle complex edge cases with confidence, because not solving is enough. While you are solving, if you want to clear the interview, you would have to be, I mean, practiced well enough about the edge cases and how to solve problems on them as well. Okay, so with that point, let's move forward. Moving forward, we are going to discuss the very first question, which is search in sorted and rotated array. So problem is, you are given with an integer array nums sorted in ascending order with distinct values, okay, not repeated, then rotated to an unknown pivot. They are rotated but we don't know from which point it was rotated to. Given a target value, then a target value is also given to you. You need to return its index if it is in the array, else return minus 1. Means you need to search for this target value in the given array, and if it is found in the array, then you need to return the index, otherwise you are going to return minus 1. Okay, constraints are the time complexity expected for the solution is order of log of n. So just to understand it in a better way, imagine someone took your sorted dictionary is sorted always, okay, the order of words in the dictionary are a to z, okay, and someone have taken it from you, they tore it in the middle and swapped the pieces, like the dictionary was from a to z, no? The dictionary was from a to z, let's say, okay, and they tore it from m to z, and they put the m to z part in the first half, and now you have a to n part in the second half, okay. Now this is your whole dictionary, complete dictionary. So it is more like the items were earlier sorted, but some part of the sorted has is still sorted, but it is rotated, है ना. पहले a to n and m to z was part of the same dictionary in this order, correct. Now someone took this m to z part and put it here, such that now the order in the dictionary has become m to z and then a to n, okay. So this has become the order in the dictionary, sorted and rotated. How do you find a word efficiently without fixing the rotation? So this problem challenges you with this problem statement. A question: how do you find a word, or you can say if it is array, how do you find an item efficiently without fixing the rotation? Because fixing rotation would cost you more time. So without fixing it, can you rightly search or not? That's what the question is, you know, without fixing the rotation. So let's see a few examples. Example 1, 4 5 6 7 8 0 1 2. You can see it clearly here that the whole array was 0 1 2 3 4 5 6 7 and 8. It's just that items from 3 to 8 have been picked and put at the front, so that the ultimate array will become 3 4 5 6 7 8 0 1 and 2. So this is how it is looking like, okay. 3 was not here, I put 3 also in the flow because the items are mostly in order, so 3 is not in the array. 0 1 2 4 5 6 7 8, it's still a sorted array, na? Ye sorted tha, and someone just picked 4 5 6 7 8 and put it in the front of the array, means at the beginning of the array, and which 0 1 2 became at the end of the array. So now this part is also sorted, this part is also sorted, and combined this whole array is now sorted and rotated, okay. Sorted and rotated array, that's what it is. And here if I try to find my target 1, so yes, 1 is gonna be there, and it is present at what index? 0 1 2 3 4 5 and 6 7. So 1 is present at the 6th index, that's why output is 6. Similarly, if I go for target 3 which is not available, so of course if I am not able to find it, then what should I be returning? Minus 1, obviously it was given in the question itself, so minus 1 would be the answer. Let's say if your array have only one item and target is 0 which is not available, so obviously the answer would become minus 1, okay, because if you can't find something you are looking for in the sorted and rotated array, then instead of returning the index which is supposed to be, but if it is not there, then you can return minus 1 directly, okay. I hope the question is clear to you. Now let's move towards how we can think and what are the observations here. Some insights are: the fundamental operation for this question is gonna be, in a rotated sorted array, at least one half left or right of the mid is always perfectly sorted. You can see it here clearly. The if the array is, let's say, 4, 5, 6, 7, 8, 0, 1 and 2, and if I divide the array in two parts, so means 0, 1, 0th index, 1 index, 2, 3, 4, 5, 6 and 7. So what would the half of it? Third index, so starting to mid, it is a perfectly sorted, yes or no? Here at least one half is sorted, that's what they are saying. At least one half is always perfectly sorted, and this particular half is unsorted. Correct, this particular half is unsorted. Similarly, for this particular example, let's see, 6, 7, 8, then 0, 1, 2, not 3, 5, 4 and 5. Okay, for this particular array, what is the mid? Mid index is gonna be same, 0, 1, 2, 3, 4, 5, 6 and 7. So mid is gonna be here, but here we can clearly see that 6, 7, 8 is sorted in itself. Sorry, till the mid we need to see, right? So 6, 7, 8 and 0 is 600 sorted tha, but आगे 0 भी आ गया, so it is unsorted. This half is unsorted, but at the same time this particular half is sorted completely. That's what our observation is. Correct. Now the strategy is gonna be find which half is sorted, because that way our idea of applying Bundy search directly would be quite much relatable, and from there we can start searching, or at least have a decision to make. Because you can see, if my target lies in the sorted part, I can search directly. If it lies in the unsorted part, then again you will see that for this 6, 7, 8 and 0, 6, 7, 8 and 0, 0, 1, 2 and 3 are the indexes, correct? If I again go with the mid part, this is the mid. Which part is sorted? Which part is sorted? Obviously this first half is sorted. So wherever you go, they will always, I mean, if it is sorted, that is completed. You can apply it directly. If target present, apply binary search directly, search directly, or go in the unsorted half and check again in the sorted, or for the sorted half. In this unsorted half, again we can see that this is sorted and this one is 780 would be unsorted. Correct? Yeah, this can be the thing. So from here we can clearly see that multiple times whenever you go in the unsorted half and you again try to divide it into two halves, you will see that one half is gonna be sorted and one half is gonna be unsorted. This way, this gives us clear idea that for every such kind of repetition we can apply binary search, because anyhow if we keep dividing the search space, it will become too short that everything will become sorted ultimately. Then there will be no part which is gonna be sorted, because if it becomes too small, then there is no two parts, and there's not gonna be two halves. Correct? So that's how we will narrow down to our target. If at the end of our whole iterations we are able to find the items, that is okay, find a target, that is okay, then you can return the index, otherwise not. We'll see more about it on the next pages. I was just setting the idea first. Okay, so find which half is sorted. This is the strategy. Check if target lies in the sorted half. Good. If yes, search there. If no, search the other half. because in the other half you will do the same thing again, you know, find which half is sorted. For this other half you will again divide it in half and find which half is sorted and do the same things. So the magic is in identifying the sorted half. Once we know that, we can make an intelligent decision about where to search. Okay, so let's move towards the thought process and algorithm development. So the same thing I have written here in form of algorithm steps properly, and with the dragon also we'll see how this is gonna work for us. Okay, so let's see very clearly. Step 1, set up search range. Search range is gonna be from 0, 1, 2, 3, 4, 5, 6 and 7. These are all the indexes of for my items. Okay, left is gonna be at 0, right is at n minus 1. So left is at this particular index, right is at this particular index. Okay, target is 1. Now binary search loop, obviously we are gonna compute the mid. So what is gonna mid? See, step 1, left is 0, right is 7, mid is 3, because 0 plus 7 divided by 2, you'll take the floor, it will be third index. So this is my mid. Okay, once I have the mid, what is the item at mid? Item at mid is 7. So I will first check if it is my target or not. Target is 1, you know, but the item is 7, so it is not the target. Okay, if it is not in the target, then I will check. Okay, like here, case number 1, middle item I am checking if it is target or not. Found, that is okay, return. Otherwise, case number 2. Case number 2, I am checking if the left half is sorted or not. So nums left less than equals to, less than equals to is shows, I mean, you can say that equal to is very important, because when the range becomes too low, okay, and your mid and left is at the same position, then this equal to is gonna matter, you know. Exactly, so nums left is less than equals to nums mid. Okay, then क्या होगा? Then we can say that this particular half is sorted, because you can see that from previous pages sorted में क्या होता था, जहाँ से शुरू हुआ है, like for this is the left, this is the mid, है ना, item at left is less than equals to item at mid, then we can say that this is sorted, this half is at least sorted. So here we can check left is sorted or not. So let's see here, 4 to 7, yes, it is sorted, है ना. So sorted half is left, that's what we have written. 4, 5, 6, 7 is sorted. Now what we are gonna do, now we are gonna check if target lies within left to mid or not. Okay, if the target lies within this sorted half or not. So it is very easy to check, because 4 to 7 is sorted, target is 1. We just need to check if 1 lies in between these two items or not. If it does, target is in there. If it doesn't, and it's clearly, we can say that between 4 to 7, if they are sorted, then 1 doesn't lie. That's why target doesn't lie here. So if target doesn't lie in my sorted half, then what do I need to do? Else search right. So I will go in the right half, okay, and do the same thing. So go to right means put our left pointer next to mid. Okay, so that's why step 2 will become what? Done step 1, step 2 will become left equals to mid plus 1, which is 4, because mid was 3. So left would come here. Okay, left abhi yahan aa gaya. Right would be at the same position, which is 7th index. Now what is the mid again? So 4 and 7, mid would be 5. Okay, 4 plus 7 divided by 5, take the floor, it will, sorry, 4 plus 7 divided by 2, take the floor, it will become 5. Now item at index 5, now mid is at index 5. Okay, the item at index 5 is 0. Now again I will see, is my left part sorted, left half sorted, or which half is sorted actually. Okay, so 4 to 5. Okay, 4 to 5, what can we say? 4 to 5, at index 4 to 5, items are 8 and 0. So are they sorted? No, because for it to be sorted, 8 should have been less than equals to 0, but it is not. That's what the idea was here. Left item at left should be less than equals to item at mid, but it is not, means left is not sorted. So we'll go where? Search right, you know, we'll go where? Search right. But at the same time we can say that अगर left sorted नहीं तो right sorted होगा. That's why I'm writing sorted half is right. Right from where? Mid to right is sorted, है ना, यहाँ से लेके यहाँ तक ये sorted है. So 0, 1 and 2 are the items which are sorted. So once we can say that left is not sorted, so we won't be doing anything in left, है ना, अब नहीं करेंगे. Sorted था, then only we were checking. Left is not sorted means right is sorted by default. So right half is sorted. Now we are in this case number 3. What we'll do? Now we'll check though right is sorted, but does my target lie in between this or not? Okay. Otherwise I would have to search into the unsorted half. Okay. So वो भी next case में आ जाएगा. Don't worry. So if target lies within nums with nums right. Okay. So what? 0 and 2. Is my 1 lying between 0 and 2? Yes, it is lying between. So there is a chance that 1 is present there. Okay. So what we can do? Yes, target lies, so we can start searching. How to start searching? How to start searching? Yeah, by moving my left boundary to mid plus 1. So left won't be here anymore. Instead left will be mid plus 1. So left will become 6. Okay, come at 6. यहाँ आ गया. That's why it is 6. So at the third step, left is 6, right is still 7. What is the new mid? 6 plus 7 divided by 2. Okay, it will become, I'm taking the flow, it will become 6. So my new mid is at this particular index 6 only. Okay, left and mid are at the 6, right is at the 7. Item at mid is 1. If item at mid is 1, you can see that I would have to check, I can check directly if the item at mid is my target or not. Correct? So yes, item at mid is my target. Nums of not 4 but 6. Okay, this should not be 4. Nums of 6 is equals to 1. Target is 1. Some typo is there. Yeah. So that's how I can say that yes, I have found it. Once I have found it, what we can do is terminate. So if it is found, it will be terminated. Otherwise, if everything is done, means now you can see that my left and mid both are at the same position. If I don't find it here, then I will go to search in the unsorted part. Okay, and I will do what? Right should be mid minus 1. So this right would become here. So this case, our left and right would cross each other. So that's where left become greater than right. So you can directly terminate the loop and say not found. Item or target that we are looking for is not available. So let's have a very clear look here in the code how this is going to be implemented. So obviously left and right are given two pointers at the edges, or can say boundaries. Left is less equals to a typical binary search, same algorithm. Mid is what we are finding. Then case 1, first we are checking if the item at the mid equals to target or not. Yes, then return directly. Otherwise check if my left half is sorted or not. So if nums left is less equals to nums mid, means the item at the left boundary is less equals to item at the mid, means till there they are sorted directly. And left half, because we found this by observing at the pattern of the problem. Okay, don't say आपको कैसे पता, वो observation से पता चला है. Okay, sorted है, then we'll apply the typical binary search idea. Then we will check if my target is greater than equals to item at left and target is less than item at mid, means target lies in the sorted half. Okay, and if it lies in the sorted half, then let's change the, or you can say reduce our search space by putting the right pointer at the mid minus 1. Okay, else target not in left half, search right half. So left would be mid plus 1. That's what we are going to do. Otherwise, means left half is not sorted, means by default right half would be sorted. अब right half sorted तो वहाँ पे भी same करेंगे. We'll try to check if the target lies in this sorted right half. If yes, then change the search space, है ना, बाउंड्री ठीक करते, देन लेफ्ट इक्वल्स टू मिड प्लस वन, टू द राइट वो हमारी बाउंड्री हो जाएगी. अदरवाइज target not in right half, search left. Okay, so for searching in left, right pointer should be equal to mid minus 1. So that's what is gonna happen, and this will keep happening until we have found a target or this loop have terminated. Okay, if we have found a target, then this mid would be returned directly and nothing would be running here from executing from here again. If we have not found the target and this loop is over, then we will directly be returning -1 representing target not found. That's all. Okay, so that will be how it is gonna work. So for this solution to work, for this working solution, the time complexity is gonna be big of log of n only. Okay, because the same binary search logic is written here. And space complexity, we have not used any much extra space in comparison to the size of the input. We have just used a few variables only, so it is going to be constant. Okay, so we can see that clearly in the complexity analysis. Time constant big of log of n, and each iteration halves the search space, same as classic binary search, nothing else. That's why. And the space complexity is going to be constant. Okay, next space have been used. Critical edge cases क्या कहते हैं? There can be single element where target can be something which is not available, so you will be returning -1, है ना. Loop runs once only. Not rotated, हो सकता है कि the array given to you is not rotated. In that case also this will be working normally, because anyway you are first checking the sorted half, and then in that half you are checking for a target. If it is not matching, then you are going in the other half. So anyways, same work is done. Okay. And rotation at start, let's say दो आइटम ही थे, स्टार्ट में ही होगा, मीन्स 1 3 was the actual order and now 3 1 is there. Again this would be, working properly, the same logic. Left half would be not sorted, would not be sorted. Yeah, target, then here target at pivot left half, or you can say right half, because the mid would be at the left only. Yeah, target at pivot, let's say the pivot item is 1, because around which you can see 2 3 sorted, 4 5 sorted. So 4 5 1 is not sorted and 1 2 3 is sorted. That's why 1 is pivot here. Okay, and target is also 1. So this is the boundary case, and this condition, the algorithm that we have written considers that also, and it captures it. But I will really ask you to practice upon these kind of try in the code that you have written on these kind of example edge cases as well. This will give you better clarity. Okay, so from this point the problem of search and sort and rotated array is over. I hope it have been very helpful way for you to understand. Now let's move to other scenario of application of binary search on a problem where you are not able to think directly where to apply a binary search. Means the search space is not clearly visible to you, because the input is not where we are going to apply the search. Okay, it is something else. That's why these problems comes under the category of abstract binary search. Okay, abstract binary search. Now the problem statement. The problem statement is, you are given an array representing the height of the trees. Okay, an array is there, so obviously there are going to be the items in the array which represents the height of the tree, and you need to cut them at a certain height that you want to determine the maximum cutting height such that you get at least m meters of wood. You need to cut them at certain height, but the height should be maximum such that you can get m meters of wood at least. Okay, in other words, you an array named trees, okay, of an integers which represents the tree height is given to you, and an integer m, means how much wood is required, is to given to you already. You need to find the maximum cutting height, which is h, such that total wood character is at least m. In short, let me show you this to you through your diagram. Most of the time people are not able to visualize what is being said. Let's say this is the array. 20, 15, 10, and 17. So how many items are there? 4. Means there are going to be 4 trees, you know? 4 trees are given. 4 trees are there. Let's draw them. So 20 is the tallest tree, okay? Let's say this is my first tree, okay? 20. This is the tallest, or should I write the index here? And this would be the height, okay? This would be the height यहाँ पे, and this is index, okay? Though Jesus should be starting from here, but I'm just starting it here. Let's for better visibility, let's remove this, you know? Just to for the symbolic representation, I mark this arrow, means this upward direction shows the height, okay? Let's say this is my 20 height, okay? Tree of height 20. Next tree is there of height 15, okay? Index 1, height is 15. I should write here, okay? There's next tree of height 10. So next tree, index 2, height is 10. Next tree of height 17, index 3, okay, height is 17, means slightly taller than the 15 height, okay? 17. Now my job is to, the question is asking me, let's say this is the ruler, okay, and this is the ruler for the heights. At what point should I mark my cutting blade such that if I cut horizontally everything, okay, so whatever falls down would be the collected amount of wood for me. So let's say if I start, okay, or mark at the height of, you can say 17, है ना? अब मैं 17 हाइट पे रूलर रखता हूँ, and this is where my blade is capped. So how much wood would be falling on the ground? Obviously this tree is 20 meters tall, okay? So 20 minus 17, because the blade is 17 meters long, 3 meters wood मिलेगा. This wood won't be touched because it is smaller. This this tree won't be touched. This tree won't be touched because it is smaller. This tree is height 17. 17 minus 17 means for it to cut it should be greater, not even equal to, okay, 0 meters. So if I put my blade at 17 meter height and cut all the trees, so I will get total of 3 meters of wood only. But what is requirement? I want at least 7 meters of wood, okay, and I need to tell what is the height at which I cut these or put my blade at, such that I will get this much amount of wood. So 17 पर नहीं मिला, then the output is saying that answer is 15. So let's try 15. Let's say if I cut my blade from here height at 15, so how much wood will I be collecting? Let's see. If I put at 15 height, the wood collected would be 20 minus 15 plus 15 minus 15 would be 0. No point in cutting it. 10 minus 15 हो नहीं सकता because this 10 is smaller, so we can't cut it using the blade if my blade is at height end at 15 meter. 17 is taller, so 17 minus 15. Okay, let's calculate total. 20 minus 15 5 plus 17 minus 15 2. Total would be of 7 meter height. Okay, so now you can see that once I try at 17, next I try at 15, you know, correct? Let's see one more example. If I tried at 13, if I tried at height 13, then 20 minus 13 plus 15 minus 13 plus 10 is still smaller, so no cut. 17 minus 13, how much total wood? 7 plus 2 plus 4, 13 meters of wood. Now I can clearly see that the more shorter distance to which I put my blade, the more wood, or you can say the shorter the distance, a height I put my blade at, more the wood I am getting, है ना? But higher the blade I am putting it, lesser the wood I am getting, है ना? 13 पे 13 meters मिला था. If I put at height 15, I am getting 7 meters. If I put more higher, I am getting 3 meters only. What is it telling you? Now you can see that clearly here. The height is gonna be from 0 till the tallest tree only. You know? And according to the wood that you are getting after cutting certain height, will tell you if you should cut at this height, or a height taller than this, or a height smaller than this. Correct? Because if you want more wood than this, then you will go down. If you want less wood, then you will go up. Isn't it showing some relation with something or some algorithm that we have learned recently? Exactly, that is a binary search. And here you can see that clearly we are not applying binary search, or not applying this idea on the given array input. We are not applying it. We are just using them to calculate the total number of wood that we will get once we decide the height of our blade. So deciding height of our blade doesn't need applying binary search on the given input array where the height of the tree is given directly. No, we would have to define our own space. How? I will show you. Don't worry. Though I have already talked about, but I will show you. Let's go to the second example first. 4, 42, 40, 26, 46. My target wood is 20. So let's say if I put it to 36 height, 4 won't be cut, 42 would be cut. 42 minus 36, 6. Correct? So 42 minus 36 is 6. 40 would be cut, 40 minus 36 would be 4. 26 won't be cut, 46 would be cut. 46 minus 36, 10. So 6 plus 4, 10 plus 10, 20. Total 20. And my target was also 20. Okay. But there can be scenario where you are getting because the height is gonna be integer, correct? So there can be scenario where you are putting the height of the blade at some integer, and the wood that you are getting is just more than what is required in the target. That is, m is 20 here, and you are getting 22 height of wood. But if you just increase the height of your blade by 1 point, you are getting lesser wood than 20. Then the answer would be the previous one, where you were getting just greater than m wood. Okay, that's why in the question they have said at least इतना तो मिलना चाहिए. थोड़ा ज़्यादा मिल जाएगा तो भी चलेगा, m से कम नहीं मिलना चाहिए. Okay, so let's move further. What is the insight here? Instead of searching for an element in the array, we are searching for the optimal answer in the range of possible answers. Possible answers is nothing but blade height range. Blade height range. Okay, blade की height का range है वो. And find the search space. As I told you earlier, we are not applying binary search on the array given in the input. Instead, we are applying binary search on the possible heights of the blade, which is nothing but yeah, the maximum height of the tree, or the tallest tree. Okay, the height of the tallest tree. So how we are identifying search space? As I showed you here, I can minimum height of blade would be let's say if the total sum of wood that I want is equal to total sum of the height of the tree, then minimum height of blade to cut this tree would be, सबको cut करना पड़ेगा, so it will be 0. And maximum मैं कहाँ तक cut कर सकता हूँ? Obviously the tallest. Correct? So that I don't need to cut anyone, because let's say the required amount of wood is 0. I don't need to cut. So blade की height क्या होगी? Blade height would be at the tallest height of the tallest tree. Okay, so max height is equals to tallest tree height. Okay, that's what it's gonna be. So let's see what is the idea. And define the search space. Lower bound 0, cut at ground level. Upper bound मैक्सिमम कहाँ सकते हैं, max tree means cut at the tallest tree height. So search space would become 0 to height of the tallest tree or max tree height. Okay. Now the monotonic property. As cutting height increases, total wood collected decreases monotonically. That's what I showed you earlier here on this particular page. What did I show you by showing these three examples? If I put at 15 the blade, okay, I was getting 7 meters. So if I want less wood, I would go upside. Okay, let's say I put my blade 17, I am getting 3 meters. The total number of wood I am getting is getting decreased if I go upwards. But if instead if I go downwards, let's say from 15 I decide to cut at 13, then I am collecting 13 meters of wood, which is greater than my wood collected at 15 meters. Means if I'm going downwards, the amount of wood collected is getting increased. That's why this is a monotonic property. Total wood collected decreases monotonically as the cutting height increases. Okay, so the strategy is somewhere around it, completely around it actually, not somewhere. Okay, the strategy is search for the optimal height h in range 0 and maximum tree height. Okay, for each candidate h, okay, h is gonna be in this range, but for every h we need to calculate total wood that we are getting. Okay, and if wood that we are getting is greater than equal to my target wood, then I will remember it and try higher height. Why? अभी greater है ना, equal to है तो भी remember किया, that is okay, वापस आ सकते, but if it is greater, remember it and go little higher so that you can see am I still getting enough wood which is meeting my target but yet less than current है ना, मतलब वो equal to m के closer आ जाए. Okay, it should go closer to equal to m, not just greater. So you can go upwards, but if wood that I am getting after cutting at height h is less than my target, then try lower height. And that's what the idea is. Okay, let's see here. Let's say these are the trees 0, 1, 2 and 3. 20 is the height, 15 is the height, 10 is the height, 17 is the height. Okay, so let's say what did I do is I decided my search space of height 0 to maximum tree. Maximum tree height among these is 20. My search space became 0 and 20. This is the low or minimum and this is the maximum. Okay, it is minimum maximum, or I can say left point of my search space and this is my right point of search space, correct? So what should I, how should I apply binary search here? I will, this search space is sorted, yes or no? Sorted search space, correct? Apply binary search, apply binary search. What is the middle? Middle would be 10. So step 1, left is 0, right is 20, middle is 10. Okay, so middle is 10, which is nothing but this is giving me the height h that I wanted to pick. So this height h I have picked as 10. How much would I get? You can see the calculation here. At height equals to 10 meters, first tree 20 minus 10, second tree 15 minus 10, third tree 10 minus 10, no wood, fourth tree 17 minus 10. Total 10 plus 5 plus 0 plus 7. Okay, 22. 22 is what? My target is 7. So 22 is greater than equal to m, which is 7, correct? तो अभी क्या करना चाहिए? I will remember this and go higher. Okay, remember h and go higher. उसको क्या करेंगे? So feasible है, would like 22 feasible because 22 is greater than equals to 7. Action क्या हो? Go higher and remember. So remembering as 10. Going higher means exactly ऐसा मानो ना कि अभी ये लेफ्ट यहाँ था एंड राइट यहाँ था, ये 20 था, ये 0 था. My mid was at 10 height. Now I know that at 10 height I am getting 22 meters of wood. I need less, but I will remember it. So I will move upwards. So this left will be at mid plus 1, है ना? तो कहाँ आ जाएगा? 11 पे आ जाएगा. Step 2, left is 11, right is 20. What is the mid? 11, 20, 21 divided by 2. So 31 divided by 2. Floor would be 15. So new mid is, this is my 11 and new mid is, let us write 11. ठीक है, new mid would be 15. Okay. At this mid, I will calculate how much would I get. 20 minus 15, 5. 15 minus 15, 0. 10 में से 15 नहीं होगा, okay, because 10 is smaller, so ये 0 ही रहने देते हैं. 7 minus 15, 2. 5 plus 2, 7 आ गया. 7 is greater than equals to 7, yes. So what will I do? Remember it, okay. Remember the height is 15. So finally remember 15, and because it's still 7 is greater than equals to 7, I'm not directly checking equal to, but I'm checking greater than equal to both. So what will I do? I'll go upwards again, है ना, कि और हाइट घटा के, मतलब हाइट बढ़ा के देखते हैं, वुड कम हो जाएगा. सो लेफ्ट वुड बी मिड प्लस 1, 14 पे 16 पे आ जाएगा लेफ्ट. So third step, left is at 16, right is at 20, mid is at 18, okay, mid is at 18. wood collected is 18 पे कितना आ रहा है? 20 plus 16, how much? 36. 18. So put it as 18. The calculation would be height equals to 18, 20 minus 18 plus 15 में से 18 नहीं जाएगा. Rest of them, no, nothing. Okay, it will become 2 only. 2 is greater than equals to 7, no, I will go down then, है ना. ये नहीं आ रहा है तो I will go down. Answer is still 15 here. Okay, go down means right would be mid minus 1. So this time you can see left is still 16, right is mid minus 1. Mid was 18, right is 17. Okay, so mid would be 16 plus 17 divided by 2, 16 आएगा floor पे. Wood collected would be what? Now let's calculate at 16. Height is equals to 16. So 20 minus 16 plus 15 won't give any wood, 10 won't give any wood, 17 would give. 17 minus 16, 4 plus 1, okay, 5 मिलेगा. Is 5 greater than equals to 7? No, नहीं है अभी. तो क्या करेंगे? अभी डाउन जाएंगे. So right would be mid minus 1 again. Okay, so left is 16, right would be mid minus 15, है ना. But here we can see that लेफ्ट हैव बिकम ग्रेटर देन, लेफ्ट देन इक्वल्स टू राइट है क्या? नहीं है अभी, बिकॉज लेफ्ट हैव बिकम ग्रेटर देन राइट. सो इट विल टर्मिनेट. सो आफ्टर टर्मिनेशन माई आंसर स्टिल एग्जिस्ट इज 15. सो दैट्स वाई 15 वुड बी द आंसर. आउटपुट इज 15 फॉर दिस पर्टिकुलर प्रॉब्लम. ओके, सो आई होप दिस इज क्लियर टू यू. बहुत ही ईजी है, because in this question the whole problem gets solved once you are able to identify a search space. उसका तो आप binary search direct लगा लेते हो. It's very easy to apply binary search once you have identified the search space. No issues. Okay, let's see the implementation here. एक feasibility function देखना था. Why? I will show you, but first focus on the algorithm. Trees are given. Target wood is given. Left we put as 0, right initially put 0, but right is nothing but the height of the maximum height tree. Okay, so find the upper bound. So for every tree in the trees array, I am checking which is maximum and updating it the right pointer. So this will give me left at 0, tallest was 20, so right at 20. Okay, now initially answer is 0. Answer I am keeping to remember what is the last height at which I was getting at least m amount of wood. Okay, now this is complete binary search. Binary search, B search I am writing short. While left less than equals to right, mid finding, then I am checking is feasible, means the mid that I have found here. Okay, so I am passing the array tree height mid height and the target, such that I am checking through this function, because this is some repeated task है ना. Every time I am selecting a height at which I am gonna cut the whole tree, I need to find how much amount of wood I am gonna get. So for that repeated task, what I am doing is I have created a function is visible. It will tell me how much wood is calculated. As you can see here, total wood I am saying. Then I am running a for loop over the whole trees array. I have target height, okay, I mean the given height that I found to the mid, and target amount of wood. So after cutting the trees which are greater than h, okay, I am calculating the total wood. If total wood is greater than my target wood, it will return, or equal to even, it will return true, otherwise it will return false. So if feasible means, if I am getting greater than equal to m wood, it will be true. If it is true means answer equals to mid. I am at least updating it here something, and then I will keep finding because I need the optimal. So लेफ्ट इक्वल्स टू मिड प्लस वन, ये लेफ्ट इसके ऊपर चला जाएगा, ओके 11 पे चला जाएगा. अदरवाइज टू मच वुड कट नीड लोअर हाइट है ना. अगर ढेर सा वुड मिल गया है, सॉरी लेस वुड मिला हुआ है, फॉल्स है यहाँ पे. अगर ये फॉल्स होता है मीन्स राइट वुड बी मिड माइनस वन, तो राइट को यहाँ आना पड़ेगा. सेम बाइनरी सर्च लॉजिक, ओके. That is what is happening here. So too much wood cut, okay, need lower height. So we will go with right equals to mid minus 1, okay. So that is how we are solving it. I think I have already shown you the triangle here, and for the same triangle we have written the whole logic. So go through it. Once this whole binary search loop is over, then we are returning the answer whatever we have, okay. So that would be all for this particular solution. I hope this is clear to you. Now clearly it is applying the binary search logic, as you can see in the sample code as well. The time complexity is big of log of n only. But for what exactly? For this particular algo it is. But what about this algo? In this particular part, okay, in this particular part we are running a for loop which is going through or iterating over the whole tree array. This is running for big O of n. इसका टाइम इतना है. So total time complexity would be, and every time I mean worst case I am gonna run it through here, okay. This is going order of n, but how many times? Log n times. So big O of log of n multiplied by n, that's what I can write. In short, multiplication हम लोग ऑर्डर चेंज कर सकते हैं. big O of n log of n. But do I really need to write the time complexity of this binary search, this particular binary search part, as log of n? Is my search space really of size n? No. If you remember from the previous page, what is my search space? Search space is not n. It's not n, but the height of tallest tree. It can be anything in comparison to n, so we can't call it n directly, so let's call it k. Let's call it k. So ultimate time complexity would become what? Ultimate time complexity would become what? Big O of n log of k. ये n ही रहेगा because we are traversing over this tree array, correct? That's why n log of k. Space complexity constant ही आएगा because we are not using any extra space here, okay. That's what is written here in the complexity analysis as well. N log k, n is the number of trees, k is the maximum tree height, okay. Space search space size, feasibility check was taking order of n, binary search was taking log of k, so that's why big O of n log k. Space complexity constant है because we are not using any extra space, okay. With the brute force, ये जो k था वो log of k would have been k directly if you have been working with a linear solution, okay. So I think in the previous session we have discussed all the number of operations. So what you need to focus upon here is this much only. Okay. Optimization tip: use long for wood total to avoid overflow. I mean, this is the implementation optimization. There are the data types: integer, then long integer. So use long int. Okay, long integer, so that you can store bigger values. Early termination is feasibility check if possible. अगर feasibility check में early termination कर सकते हैं, so it will save you some time. Okay, careful with boundary conditions, because most people, I mean, overutilize these things. वो उसको optimize नहीं करते हैं. So if you optimize there also, you will get to solve the question in lesser time. Okay. Now, pattern recognition framework. So when to use binary search on answer? I mean, the way we have discussed it on the last problem. So mostly it happens with the optimization problems, finding maximum, minimum, x such that y condition holds. Some condition needs to be held. So example is a woodcutter. Aggressive cows question is also out there in the lead code. You can look at that. Monotonic function, like it was present in this current problem as well, where increasing the height of the machine was decreasing the amount of wood collected, and vice versa. Function fx increases or decreases with x. That's what was happening. ये ऐसा और कहाँ होता है? Square root question is there, capacity of ship question is there. In these questions it happens. Search space known. Answer lies in predictable range. Okay, so we had to find out the space first, है ना? Search space, then ये आज के सारे प्रॉब्लम्स पे लगा था. Okay, decision framework. How do you decide? So can I define a search space for the answer? If you can answer this question, it will give you better clarity around how to solve this, how to figure out the search space. Is there a monotonic relationship like this? It will give you some hint. Yes, you will become more sure around applying this kind of solution. Can I write a feasibility function? This will, I mean, reduces a lot of task, है ना? For I can say for repeated task, because एक बार लिखोगे and बार बार ये calculate कर रहा होगा for repeated task and avoiding unnecessary work. Unnecessary job. Okay, if yes, binary search on the answer, you can apply. Okay, next is real world applications and variations. So of course this is a very strong algorithm and the applications are strong as well. So in real life they must have been used. So in e-commerce, optimal pricing strategies. Okay, this is where this logic is used. Binary search on answer. प्रॉब्लम पैटर्न क्या है? जो अभी हमने देखा कि वो आंसर पे बाइनरी सर्च लगा था, नॉट ऑन द इनपुट एरे. इंस्टेड द बाइनरी सर्च वाज बीइंग अप्लाइड ऑन द आंसर. इन लॉजिस्टिक्स फील्ड, शिप कैपेसिटी ऑप्टिमाइजेशन, वुड कटर वेरिएंट. ओके, इज व्हाट वी हैव सीन. एग्रीकल्चर रिसोर्स एलोकेशन में यूज़ होता है. सिमिलर ऑप्टिमाइजेशंस, I mean similar problems, optimization problems, you can look on the lead code, you can solve it. Text system parameter tuning. So we are always craving, or you can say looking for the optimized part. So parameter tuning is one of them. Rotated search variants is one of the questions you can solve for this. Popular interview variations में क्या आता है? Means in the Google and Meta company, what have been asked? Search in rotated sorted array 2 with duplicates. Here we worked upon the, you can say, distinct item, but another version would be when duplicates are there, then how you can apply. So you can try solving this also. Find minimum in rotated and sorted array. So the way we were doing a search, okay, similar kind of logic is gonna be applied to find minimum in sorted and rotated array, because minimum item is greater than its right neighbor. That is the logic. Okay, I am giving you a hint. And greater than its left neighbor as well. Okay, so you can work upon it. Next is capacity to ship packages within D days. Okay, so time is given. Okay, and in this problem something regarding the capacity would be asked. So I will say this is similar to this problem, ship capacity optimization. Okay, you can try solving it on the lead code also, and you will get better, you can say, visibility. In Amazon and Microsoft, there is another question called aggressive cow. This is also available, you can try solving it. Was asked classic binary search on answer, split array largest sum, Cocoa eating bananas, very popular question. You can try solving this as well. Okay. So after solving these, I would say after learning these, I would say you can take few problems as homework. And if you want to just strong your foundation, you can implement both problems three times from scratch using pen, paper, and applying. And then implementing on the IDE as well. Done with all provided examples and explain algorithm to peers. Because explaining things that you learn to others would make it better in your mind as well. It will the chance of forgetting it will be very less. Okay. Application. So finding minimum in a rotated sorted array. Capacity shift we talked about. Aggressive curves we talked about. You can solve these things. And mastery के लिए search in sorted array 2 means with duplicates. You can try solving this. Co-creating banana, very popular question. Split array largest sum. These are the same questions that have been asked in FAANG companies, so you can try these as well. Now in the next session, what we are going to do? We are going to work with find the duplicate number using binary search. Obviously, we have been working on the distinct numbers. In next session, we'll work around duplicates as well. Okay, to show you how binary search can be used on a non-array index context, but on the value range as well. Next, problem 2, capacity to ship package in details. You can try on your own also. Anyways, I'm gonna discuss this in the next session as well. So these are the two questions that I will be discussing in next session. So please come prepared. Things would be very interesting. Interactive Q&A and file motivation. So test your understanding. How would you modify rotated search if duplicates were allowed? Means, see, learning is a part where you just don't go to the answer, apply, and if it is successful, you will sleep. No. You need to ask a few pointed questions to yourself to check your understanding as well. So the questions would be, how would you modify rotated search if duplicates were allowed? This will give you a hint for working with the next question, where you need to search in sorted and rotated array, but the duplicate items are allowed. In woodcutter problem, what if we needed exactly m wood, not at least m? Then what modification would you do in the solution? Can you think of another real world problem that uses these patterns? Okay. Challenge problems. Implement rotated search with recursion instead of iteration. Okay. So we have been implementing it using loops, but can you do it using recursion? Try to do that. Solve woodcutter problem when trees can have negative heights as well. Then how would you work with it? Find it out. Okay. Design test cases that would break these implementations. Best part of learning. File motivation. So every complex algorithm you master and every optimization pattern you learn, this is gonna build your confidence, build your thought process, and the more you solve it, the more you try to retain it in your mind, the better intuition it is gonna give you. Intuition will be built, and somehow you won't have to recollect things, you will be able to solve it directly. That's what intuition is. That comes with the repeated you can say practice. Okay, and ultimately your confidence would be increased too much. So you are not just preparing for interviews, you are building the problem solving skills that will define your engineering career. Okay, better at here, better would be everywhere. That's what the motto. Okay, so that's all for today everyone. Let's meet in next session. If you have liked this video, please like, share and subscribe. Let's meet in another session from Aarush coaching classes. Okay.